Nature of matter. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. They have mass and they occupy space. States of matter. Matter can exist in three physical states, namely solid, liquid, and gas. Particles are held very close to each other in solids in an orderly fashion, and there is not much freedom of movement. In liquids, the particles are close to each other, but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. 1. Solids have definite volume and definite shape. 2. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. 3. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. Solid with heat becomes liquid, which with heat becomes gas. Gas, when cooled, becomes liquid, which when cooled becomes solid. On heating, a solid usually changes to a liquid, and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling liquefies to the liquid, and the liquid on further cooling freezes to the solid. Classification of matter. At the macroscopic or bulk level, matter can be classified as mixture or pure substance. When all constituent particles of a substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it in any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture, and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixtures. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout, and sometimes different components are visible. For example, mixtures of salt and sugar, grains and pulses, along with some dirt, often stone pieces, are heterogeneous mixtures. The components of a mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixture. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water, and glucose are some examples of pure substances. Glucose contains carbon, hydrogen, and oxygen in a fixed ratio, and its particles are of the same composition. Hence, like all pure substances, glucose has a fixed composition. Also, its constituents, carbon, hydrogen, and oxygen, cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. They all atoms are of one type. However, the atoms of different elements are different in nature. Some elements such as sodium or copper contain atoms as their constituent particles, whereas in some others, the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen gases consist of molecules in which two atoms combine to give their respective molecules. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. The atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, that is water, is a liquid. Properties of matter and their measurement. Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acids and bases, etc. Physical properties can be measured or observed without changing the identity or composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter, such as length, area, volume, etc., are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6m. Here, 6 is the number and m denotes meter, the unit in which length is measured. The International System of Units SI. The International System of Units, in French, Le Système International de Units, abbreviated as SI, was established by the 11th General Conference on Weights and Measures, CGPM, from Conference General des Poids et Mesures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities: mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass is kilogram. However, its fraction, named as gram, 1 kilo is equal to 1000 grams, is used in laboratories due to the smaller amounts of chemicals used in chemical reactions. Volume. Volume is the amount of space occupied by a substance. It has the units of length raised to 3. In SI system, volume has units of meter cube. In chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in centimeter cube or dm cube units. A common unit liter L, which is not an SI unit, is used for measurement of volume of liquids. 1 L is equal to 1000 ml. 1000 centimeter cube is equal to 1 dm cube. Density. Density is equal to mass divided by volume. Density of a substance is its amount of mass per unit volume. So, SI units of density can be obtained as follows. SI unit of density is equal to SI unit of mass divided by SI unit of volume, which is equal to kilogram divided by meter cube or kg m raised to minus 3. This unit is quite large, and a chemist often expresses density in gram per centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. Temperature. There are 3 common scales to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. K is the SI unit. Generally, the thermometer with Celsius scale are calibrated from 0 degrees to 100 degrees, where these two temperatures are the freezing point and the boiling point of water respectively. The Fahrenheit scale is represented between 32 degree and 212 degree. The temperatures on two scales are related to each other by the relationship. Degree Fahrenheit is equal to 9 divided by 5 degree Celsius plus 32. The Kelvin scale is related to Celsius scale as K is equal to degree Celsius plus 273.15. Temperature below 0 degree Celsius, that is negative values, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. Scientific notation. Chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers. This problem is solved by using scientific notation for such numbers, that is, exponential notation, in which any number can be represented in the form capital N into 10 raised to small n, where small n is an exponent having positive or negative values, and capital N is a number called digit term, which varies between 1.000 etc. and 9.999 etc. Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus 1 which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 ml, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus or minus 1 in the last digit. unless otherwise stated, an uncertainty of plus or minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. 1. All non-zero digits are significant. 2. Zeros preceding to first non-zero digit are not significant. Such zero indicates the position of decimal point. 3. Zeros between two non-zero digits are significant. 4. Zeros at the end or right of a number are significant provided they are on the right side of the decimal point. But if otherwise, the terminal zeros are not significant if there is no decimal point. Such numbers are better represented in scientific notation. 5. Counting the numbers of objects, for example, 2 balls or 20 eggs, have infinite significant figures as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal. In numbers written in scientific notation, all digits are significant. Example, 4.01 into 10 raised to 2 has 3 significant figures and 8.256 into 10 raised to minus 3 has 4 significant figures. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. One has to keep in mind the following points for rounding off the numbers. 1. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. 2. If the rightmost digit to be removed is less than 5, the preceding number is not changed. 3. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. Laws of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. Law of conservation of mass. This law was put forth by Anton Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached the conclusion that in all physical and chemical changes, there is no net change in mass during the process. Hence, he reached the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. Law of definite proportions. This law was given by a French chemist, Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Irrespective of the source, a given compound always contains same elements combined together in the same proportion of mass. It is sometimes also referred to as law of definite composition. Law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. Gay-Lussac's law of gaseous volumes. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportions by volume. The law of definite proportions stated earlier was with respect to mass. Avogadro's law. In 1811, Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules. Avogadro could explain the above result by considering the molecules to be polyatomic. Dalton's atomic theory. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. 1. Matter consists of indivisible atoms. 2. All atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. 3. Compounds are formed when atoms of different elements combine in a fixed ratio. 4. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination. However, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. Atomic and molecular masses. Atomic mass. The atomic mass or the mass of an atom is actually very, very small because atoms are extremely small. Today, we have sophisticated techniques, example, mass spectrometry, for determining the atomic masses fairly accurately. The present system of atomic masses is based on carbon-12 as the standard and has been agreed upon in 1961. Here, carbon-12 is one of the isotopes of carbon and can be represented as 12C. In this system, 12C is assigned a mass of exactly 12 atomic mass unit AMU, and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of one carbon-12 atom. 1 AMU equals 1.66056 into 10 raised to minus 24 grams. Mass of an atom of hydrogen equals 1.6736 into 10 raised to minus 24 grams. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements, average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, percent occurrence, the average atomic mass of that element can be computed. In the periodic table of elements, the atomic masses mentioned for different elements actually represent their average atomic masses. Molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. Formula mass. Some substances such as sodium chloride do not contain discrete molecules as their constituent units. In such compounds, positive sodium ion and negative chloride ion entities are shown in a three-dimensional structure. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state, sodium chloride does not exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine. Mole concept and molar masses. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. We use the idea of mole to count entities at the microscopic level, that is, atoms, molecules, particles, electrons, ions, etc. In SI system, mole, symbol MOL, was introduced as seventh base quantity for the amount of a substance. The mole, symbol MOL, is the SI unit of amount of substance. 1 mole contains exactly 6.022 into 10 raised to 23 elementary entities. This number is the fixed numerical value of the Avogadro constant Na when expressed in the unit per mole, or is called the Avogadro number. The amount of substance, symbol small n, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle or specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities no matter what the substance may be. In order to determine this number precisely, the mass of a carbon-12 atom was determined by a mass spectrometer and found to be equal to 1.992648 into 10 raised to minus 23 grams. Knowing that 1 mole of carbon weighs 12 grams, the number of atoms in it is equal to 12 grams per mole 12C divided by 1.992648 into 10 raised to minus 23 grams per 12C atom equals 6.0221367 into 10 raised to 23 atoms per mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is known as Avogadro constant or Avogadro number, denoted by capital N, capital A, in honor of Amedeo Avogadro. The mass of 1 mole of a substance in grams is called its molar mass. The molar mass in grams is numerically equal to atomic or molecular or formula mass in U. Percentage composition. Mass percentage of an element is equal to mass of that element in the compound into 100 divided by molar mass of the compound. Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molar mass is known. Stoichiometry and stoichiometric calculations. The word stoichiometry is derived from two Greek words, stoichion, meaning element, and metron, meaning measure. Stoichiometry thus deals with the calculation of masses, sometimes volumes also, of the reactants and the products involved in a chemical reaction. Limiting reagent. The reactant which gets consumed first limits the amount of product formed and is therefore called the limiting reagent. Balancing a chemical equation. According to the law of conservation of mass, a balanced chemical equation has the same number of atoms of each element on both sides of the equation. Many chemical equations can be balanced by trial and error. Subscripts in formulas of reactants and products cannot be changed to balance an equation. Reactions in solutions. The concentration of a solution or the amount of substance present in its given volume can be expressed in any one of the following ways. 1. Mass percent or weight percent, W by W percentage. 2. Mole fraction. 3. Molarity. 4. Molality. 1. Mass percent. Mass percent equals mass of solute divided by mass of solution into 100. 2. Mole fraction. It is the ratio of number of moles of a particular component to the total number of moles in the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given as mole fraction of A equals number of moles of A divided by number of moles of solution equals Na divided by Na plus Nb. Mole fraction of B equals number of moles of B divided by number of moles of solution equals Nb divided by Na plus Nb. 3. Molarity. It is the most widely used unit and is denoted by capital M. It is defined as the number of moles of the solute in 1 liter of the solution. Thus, molarity M equals number of moles of solute divided by volume of solution in liters. 4. Molality. It is defined as the number of moles of solute present in 1 kilogram of solvent. It is denoted by small m. Thus, molality small m is equal to number of moles of solute divided by mass of solvent in kilogram. Often, in a chemistry laboratory, a solution of a desired concentration is prepared by diluting a solution of known higher concentration. The solution of higher concentration is also known as stock solution. Note that the molality of a solution does not change with temperature since mass remains unaffected with temperature. Summary. Chemistry, as we understand it today, is not a very old discipline. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter, which can exist in 3 states: solid, liquid, or gas. The constituent particles are held in different ways in these states of matter and they exhibit their characteristic properties. Matter can also be classified into elements, compounds, or mixtures. An element contains particles of only one type, which may be atoms or molecules. The compounds are formed where atoms of 2 or more elements combine in a fixed ratio to each other. Mixtures occur widely, and many of the substances present around us are mixtures. When the properties of a substance are studied, measurement is inherent. The quantification of properties requires a system of measurement and units in which the quantities are to be expressed. Many systems of measurement exist, of which the English and the metric systems are widely used. The scientific community, however, has agreed to have a uniform and common system throughout the world, which is abbreviated as SI units, International System of Units. Since measurements involve recording of data, which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurements of quantities in chemistry are spread over a wide range of 10 raised to minus 31 to 10 raised to plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care of by specifying the number of significant figures in which the observations are reported. The dimensional analysis helps to express the measured quantities in different systems of units. Hence, it is possible to interconvert the results from one system of units to another. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportions, law of multiple proportions, Gay-Lussac's law of gaseous volumes, and Avogadro law. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to 12C isotope of carbon, which has an exact value of 12U. Usually, The atomic mass used for an element is the average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular mass. The number of atoms, molecules, or any other particles present in a given system are expressed in the terms of Avogadro constant 6.022 into 10 raised to 23. This is known as 1 mole of the respective particles or entities. Chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lot of information. The coefficients indicate the molar ratios and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactants required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of a solution is expressed in a number of ways. Example, mass percent, mole fraction, molarity, and molality.